Hi everyone. In this supplemental video, I'm going to explain one more mathematical trick that we can use within differential geometry to make our calculus of partial derivatives a little bit stronger. And that trick is called the Maxwell relation, or a Maxwell relation, and the set of them would be then called Maxwell relations. Now, of course, this is named after a famous dead guy, so you know that it must either be very simple or very important. In this case, it's very important and moderately simple. So what we have here is actually just the statement that the second derivatives of a function commute. So if we have a function, for instance, xy, then you'll be very familiar with the idea that we can commute, oops, that should have been a y. We can commute the order of the partial derivatives. So we can either take the y derivative first or the x derivative first. Okay. Well, we want to exploit the same kind of thing, but now we're going to focus on the free energies. So let's write our thermodynamic identity for the Helmholtz free energy. We saw that dF is equal to minus S dt minus P dV plus mu dN. And in particular, this means that the partial with respect to t of F while fixing V and N is equal to minus S. Good. Now we also have that the partial with respect to V of F while fixing T and N is equal to minus P. Very good. Maxwell relations come when we need to take derivatives of these kinds of objects. So we're taking derivatives of the functions that appear as coefficients of these basis 1 forms. What we get from these two is the following. So dt fixing v and n, and then, oops, let's move this over a little bit. And then dv fixing t and n is the same as on the inside, dv of f fixing t and n, and on the outside, dt dt fixing v and n. All right, wonderful. But now we can simplify these by the relations to the left. So dt of f fixing v and n is minus s. dv of x fixing t and n is minus p. And so we get that minus dv of s fixing t and n is equal to minus dt of p fixing v and n. Now you may recognize this identity from lecture 9. In particular, the supplemental video in which I talked about the way that we know that the heat capacity at constant pressure is greater than the heat capacity at constant volume. There, we needed to use this Maxwell relation in order to simplify our lives. So why does this normally occur? And why did it occur in that case? Well, the answer is that when we think about what we can experimentally measure, it would more typically be objects like this. Objects that involve temperature, pressure, volume. These sorts of objects are easy to measure in the lab. On the other hand, entropy is quite hard to measure in the lab, and chemical potential can be challenging as well. And so we'll often want to take some derivative of entropy and turn it into a derivative of something easier to work with. Good. The key here is that we can actually also combine this with our other calculus identities. So combine this with the triple product rule and with the inverse function rule or inverse function theorem. And combining these three, we can do a lot of different manipulations. In fact, I quite like this chart, which is from the Wikipedia page Maxwell Relations. That shows this relationship. So this derivative can be turned into a product of these two derivatives by the triple product rule. And you can convince yourself of that quite quickly. So dps, let's move things in this direction. So dps v d vs, oops, nope. So we're going to move this down. ds v p is equal to -1. Or if we want to express this in terms of the other two, we would have to move them to the other side. So this implies partial vp fixing s is equal to, so we flip this and this because of the inverse function theorem. So cursor is not working. dsp fixing v times dvs fixing p, just as we see here. Then, using the Maxwell relation, we can turn this object into this object. And in fact, the one that I just showed you is the one where we fix partial s, partial v, and partial p, partial t. So this is the one that we just saw. And you'll see here that in this diagram, the author reduces these types of quantities that are at these ends and that are given names up here. You'll notice if you watch that supplement that we have the isothermal compressibility and the thermal expansion coefficient right here. And these are the kinds of things that we would be able to measure quite easily with most lab equipment. So with that, we have a very complete picture of how we might manipulate these partial derivatives into things that are easier for us to work with. That's really all I had for this one. Thank you so much for watching, and I'll see you in the next one.